changed the timer. I think this is the largest number of screens that I've ever seen in my life. So my name is Alexander Barg, and I'm an electrical engineering and Institute for Systems Research, also an affiliate professor in computer science and in mathematics. And I present a talk about one of the problems that has been interesting me in the last few years. Generally, I work, my research is in applied mathematics with focus in information theory and in a number of neighboring areas. And the question that I'm considering here is motivated by distributed storage, which I will mention in a moment. But let me just start with the following problem. Suppose we have a polynomial f, which is defined over some field, let us say finite field, which I denote here by f. Let's say the degree is k, and let us say we have evaluated that polynomial at endpoints of the field denoted p1, pn here. Now let's say one evaluation is missing, f of pi. At how many values do we need to look? At how many evaluations do we need to look to be able to recover that missing value? The question is, of course, loosely formulated, and the answer that comes to mind, we need to look at k plus 1 evaluations to recover the entire polynomial. But is it possible to construct a large set of polynomials for which we can recover f of pi by looking at a small number of evaluations? So that's a question that comes from distributed storage. And distributed storage, I'm told, looks like this. These are those racks that carry hard drives, maybe even at Facebook mentioned recently. And of course, those drives fail, and what we need to do is to be able to ensure data integrity in the face of those failures that occur on a daily basis. So let us say this large volume of data is spread between the drives, and current solutions for keeping the data available are either replications or what they call Reed-Solomon codes, a particular way of encoding the data. Under replication, we just take the data and write it 3 times on 3 different drives. If a drive is missing, is dysfunctional, then we turn to the functional drive and copy the data. And this is a reasonable solution, except for the storage overhead by a factor of 3, which, of course, with the increase of the number of data, becomes unsustainable. And a competing solution is to use an encoding of the data, what is called an MDS code, doesn't matter what that means. So we take 3 packets, 3 chunks of data, and encode them into 5. And then to recover the missing drive, we look at any 3 functional drives and recover the data. And so the storage overhead is now 5 over 3, which is 1.67, which is better than under replication. Although at the same time, to recover the drive, we'll need to communicate more data across the system to complete the task. So we are facing 2 extremes. One is the storage overhead, the other is the communication overhead. And our task is to design something in the middle. So that is how distributed storage motivates the problem that I mentioned on my first slide. This does not move anymore. I don't know why. See, I don't know what to do now. What did you do?
I moved the mouse there.
Oh, that's an embarrassment. So Reed-Solomon codes, let us talk about them for a while. Let us say we are encoding 4 chunks of data, A0 to A3. And to encode them, we write a polynomial over the field that we have in the background, the polynomial of this form. We evaluate that polynomial at endpoints of the field, and thereby we obtain a code word and encoding for these four symbols of the field. So this is my polynomial, and the points on the graph collectively represent the code word of the Reed-Solomon code. Of course, the polynomial is of degree 3, so the number of zeros is at most 3, so the Hamming weight is large. and the distance, therefore, between any pair of code words is large, and so that's how we construct good codes. By running over all the possible coefficients A0 to A3, we obtain the collection of code words that collectively form a Reed-Solomon code. So let us say one drive is missing, which is here indicated by this bold blue point. A way to recover that missing data is to turn to any k points on the graph. Yeah, polynomials were of degree k plus 1, k points suffice. Then it gives us the missing data, but in fact it gives us much more than we need. It gives us the entire polynomial. Is it possible to look at fewer evaluations to recover the missing drive? This is my last line here. For that, we could design a carefully chosen subset of polynomials so that, let's say, restricted to a small subset of points, my large degree polynomial of degree k becomes a low degree polynomial. And then I can interpolate from that low degree. So if that is possible for every point on the evaluation, I've accomplished my goal of recovering the data. Let me run an example. So let us say I'm encoding 4 chunks of data into n symbols. So my code is of length 9 and it encodes 4 symbols of the data. Let us say my set of points over the field of 13 elements is from 1 to 12, so all computations are modulus 13. Let us say I split the points into 3 disjoint groups, shown here A1, A2, and 3. I take my message, and this is my polynomial space. Let us, for instance, take A1, the 4 pieces of the data to be all ones, so my polynomial is as shown here, 1x, x cubed, x4. I evaluate that polynomial at the points of the set A on the second line, and I get this vector of length 9, so I put those chunks on separate drives. And let us say the first of these evaluations, the first drive is dysfunctional, so the 4 is missing. So then I access the evaluations of the polynomial at the points in the same group, A1, F3, and F9, and I interpolate a low degree polynomial which happens to be 2x plus 2. This 2x plus 2 indeed evaluates to 4, 8, and 7 at the points of A1. So I compute C1, the data on the missing drive, as the value of this low degree polynomial at 1. So that is how this algebraic task can be solved. And this is a start of a rather large set of problems. Again, motivated by distributed storage, but addressed by methods of applied algebra. A related question could be, what if we now store our information on a graph with the requirement that, so we store those chunks of symbols on a graph, and the data at every vertex should be recoverable by looking at a set of neighbors of that vertex. So not only communication constraints, but also connectivity constraints in the network. And then the questions about the maximum amount of information can be asked. Can be stored on a graph under this constraint of local recovery. And which coding schemes attain the limit, the maximum amount of information. That's a related problem addressed by a rather different technique and facing different set of challenges. To obtain more information, I recently gave a tutorial on erasure coding for distributed storage related problems. So there is this website, North American School of Information Theory, and it's actually 3-hour tutorial with, of course, YouTube video and whatnot. So it is accessible. And this semester I'm teaching a course in a different area. It's called Modern Discrete Probability. So it's applied probability with applications in random graphs, networks, and so forth. I'm a little bit cautious in advertising it here because I already have about maybe 12, 14 students from computer science. I don't know if I want that larger class, but nevertheless I'll mention it. Thank you.